I'm Meghamala, working as Assistant Professor from Electronics and Communication Department, Institute of Aeronautical Engineering. So, welcome to the topic. Today's topic is about designing examples using behavioral modeling. So, here in this particular topic, we will discuss some examples. Okay, in the already pertaining to this module 3, we have discussed regarding the topic wise, we have discussed only few examples, but here in this presentation we will discuss more about the examples in all the aspects. Okay, so here the first one is coming to the example based on using continuous assignment statement. So here, this is a particular example where we will see the continuous assignment statements. Already, we have discussed what is a continuous assignment statement. Coming to this assignment, what is mean by assignment? Assignment is nothing but dumping some values onto a variable. Okay, this is what we have learned. So, dumping some value onto a variable is nothing but the assignment. So, in the Verilog, when you are writing some code in the syntax form, we need to assign some values, isn't it? We need to assign some values to the variables. So, this is nothing but the assignment. For example, my inputs are A, B and C. Okay, and then now I wanted to give some values. So, I want to initialize some values onto these inputs A and B. So, what will I do? A is equals to 10, this is what I am giving. B is equals to 20 and C is equals to 30. So, this is nothing but the assignment. And here coming to continuous assignment statements. We do have discussed not only the continuous assignment statement but also different kinds of statement based on the nets. Okay, based on the nets, based on the delays, based on the operators. So, different kinds of continuous assignment statements, declaration statements and so on. Okay, so here when it comes to the continuous assignment statement, this is an example, module adder. So, here module is a keyword. So, we already discussed in the Verilog, we have some keywords, isn't it? So, few keywords are module, end module, if, begin, end, isn't it? So, these are all nothing but the keywords. So, for any kind of program that you are writing, the syntax form, if you are starting it with the module keyword, it must be end with the end keyword. Okay, if you are starting something in between the sentence, if you are starting your exact programming, the programming should start the statements pertaining to that particular designing, particular module. You have to mention the statements in between two keywords, that is begin and as well end. So these are the keywords, different kinds of keywords where are used in order to write the syntax. So here under continuous assignment statements, what we see module. The module that I'm considering is adder. So here in this adder, my inputs are 31 is to 0. So here totally 32 bits of information that I'm going to get in terms of like my input of one of my input is 32 bits and one of my input is AB is 32 bits again. So here is my input 1 and here is my input 2. So how many kinds of bit I'm using here? 31 is to 0. So here 31 is to 0, 31 is to 0. So my output would be same to 31 is to 0. At the I'm representing Y with output A and B are the input. And then here using the assign keywords. So pertaining to the different module, we have discussed like in the Verilog, there are 4 kinds of leveling modeling styles. There are 4 types of modeling styles we have discussed. One is data flow. Okay, and the next one is gate level modeling, behavioral and switch level or circuit level, isn't it? So these are the 4 different modeling styles. These are module modeling styles. So when it comes to among these 4 modeling styles, we see behavioral is having a highest abstraction modeling. we can say that behavioral modeling is nothing but a higher of abstraction modeling. Another name for behavioral modeling is also called as algorithmic modeling. Okay, another name for behavioral modeling is algorithmic modeling. So when it comes to behavioral modeling, there are certain types. When you are writing some syntax pertaining to all this behavioral modeling, each and every modeling will have some keywords, okay, basic keywords. So based on that keywords, we can easily identify what kind of modeling style it is. So here, when it comes to behavioral modeling, always at the rate. In the behavioral modeling, the keyword that we use always at the rate, isn't it? And then in the data flow modeling, assign is a keyword. So here in this continuous assignment statement, okay, in the continuous assignment statement, we are going as per the gate level or else a data flow, as per the data flow. Data flow is nothing but the flowing of information or it's a transfer of information from one register to the another register is been taking place. That means what? The transfer of data between the registers. So here in this particular transfer of information between the registers, we are using a method called RTL, the register transfer language. Okay, so using the register transfer language method, we can easily transfer the data between one register to the another registers or else one module to the other modules and so on. So here, as we are discussing the continuous assignment statement, so we need to consider the keyword is assign. So here, assign y is the output. So assign y is equals to a plus b. Okay, I'm adding, simply I'm considering the modulus adder such that I'm adding y is equals to a plus b. And then finally, I'm ending up or else I'm terminating the syntax with the end module. Okay, so this is a basic way of how to write a syntax based on the continuous assignment statements. And the second one is using bitwise operators. So here in this bitwise operators, already we have discussed few bitwise operators. Arithmetic, logic bitwise operators, arithmetic bitwise operators, relation bitwise operators. Okay, arithmetic, logic. So the conditional bitwise operators. So these are the few bitwise operators, and here we will see an example of how to write a syntax based on the bitwise operators. So here I am considering bitwise operations acts on vectors. Already we have discussed about the scalars and the vectors. What is a scalar and what is a vector? Okay, so for example, scalar is nothing but they represent a one bit of information, and the bit which is carrying a one bit of information, they are very suitable and very suitable for the transfer of data from one circuit to another circuit in a bitwise or a single bit. Whereas here in the vector representation, what does it mean by vector is, vectors are nothing but the group of bits. Okay, for example, in my register, I'm having bits of 10:0. That means was totally 11 bits of information I'm having. So what should I do if I want to transfer from one circuit, from circuit 1 to circuit 2? If I want to transfer the bits, how will I transfer? There are two ways of transferring the bits. One is a single line of transferring, and the second one is a cluster of bits, transfer of cluster of bits. So if you are transferring a single bit, that is r is equals to 0 bit, r is equals to 1 out of 10. If you are transferring single bit from r is equals to 0 to 10, okay, 0 to 10, this is nothing but the vectors. Okay, so all together, all the bits I'm storing in a register, that is 10 is equals to 0. So this is what we will observe when it comes to the vector, bitwise operations on vectors. So here, module. Here I am considering the circuit diagram, or else a basic circuit, digital circuit that I am considering is inverter. We all know what is an inverter, right? Inverter is, if you are giving 0, the output will obtain is 1. If you are giving 1 and output we get is 0. It's quite opposite. Okay, so module, inverter, my inputs are 3:0. That means of total 4 bits of information A, and the output is also 3:0 as well Y. For example, my inputs are 0, 0, 1. If these are my inputs, okay, 0, 0, 1, 1. And what will I get in the output when it comes to the inverter? I'll get 1, 1, 0, 0. Isn't it? 1100. Okay. So here bitwise operator, for this I'm assign output y. Y is an output. Output is equals to, as it is an inverter. So what kind of operator that we need to consider is negation. Not. Isn't it? Bitwise operator, not of A. So end module I'm terminating. So this is an example when it comes to how to write a syntax in the when it is a bitwise, using a bitwise operators. Okay. So here negation not, and, or, and all. With all this you can also write down the syntax when it comes to the bitwise operator. And coming to more bitwise operators. What does this more bitwise operators mean? So here, as I said you, we consider the bitwise operators on vectors, isn't it? Or buses. So here, I'm considering the module gates. I'm considering now the gates. Okay. So what would be my inputs and outputs? As I said you, this is a module is a keyword, and gate is nothing but the what kind of combinational circuits that you are considering mention. We need to mention here with the name. And then in the brackets, these brackets are nothing but the port list. Okay, bracket is nothing but the port list. What is a port list? Port list always considers the input and as well as the output ports and in-out ports. Okay, input, output and in-out port. But when you are representing in the port list the input and output and in-out ports, always remember that output port should come first and then followed with the input ports and then followed with the in-out port. So output ports should come first and then followed with the input ports and then followed with the in-out port. So this is how we need to represent the port list. Then in the module gates, these are the inputs, 3:0 of bits A and B, and output is as well 3:0 Y. My outputs are Y1, Y2, Y3 and Y4, Y5. Okay, so totally 5 kinds of information, 5 bits of totally 5 gates that I may getting using the gates. I may observing my output would be 0, 1 to 5, totally 5. And then the 5 different 2 input logic gates acting on 4-bit buses. So here the comment and also remember this, when you are writing a syntax or a program, always remember that to write the comments. Okay, you all know when it comes to the comments, already we have discussed, we have about the single line comment. Okay, single line comment and as well double line comment. Isn't it? So single line comment is nothing but start with ash and star and end with ash and star. End with ash and star. And then for the double line comments, star, star. Isn't it? So this is how the comments will be made or else passed in the when you're writing some when you're writing some program. So here, as per this example, 5 different 2 input logic gates. So these are the 5 different, how many inputs? 2 inputs, isn't it? So these are the 2 inputs logic gates acting on 4-bit buses. So here, these are acting on the 4-bit buses. How come 4-bit buses? My input is 3:0, isn't it? So it's totally 4-bit. So acting on 4-bit buses, how the outputs from 1 to 5, Y1 to Y5 is observing, we will see. So here, as per this, assign Y1. What is this Y1? Where is my Y1? My Y1 is over here. So this is my Y1. So Y1 is equals to which AND gate? Output of AND gate, isn't it? Y1. This is the AND gate. So Y1 is equals to A and B. So this is an AND gate. Done. And then assign Y2, output Y2. Y2 is A or B. Where is my Y2 here? My Y2 is over here. Or this is AND. So output is OR gate, right? So Y1, Y2 is equals to A or B. This is done. And then assign Y3. Y3 is XOR. Where is my Y3? Y3 is over here. So this is XOR gate, isn't it? Then Y4 is NAND gate. This is my Y4, which is nothing but the NAND gate. You know what is NAND. AND plus NOT is nothing but the NAND. So here when you observe, this is a AND gate. AND gate is again given on to the NOT gate. So AND plus, this is AND plus NOT, which is nothing but the NAND. So negation NAND, how will I write? Not, I have come with the NOT, right? So NOT of A and B, isn't it? So NAND gate. Similarly, Wi-Fi. Wi-Fi is nothing but the OR gate, NOR gate, isn't it? So Wi-Fi is NOR gate, a negation of A or B, and N module. So this is a simple example when you want to write something, when you are developing some module based on the gate level behavioral gate level modeling. You need to assign all the gates with respect to the inputs and all the outputs. You have to write the expression. Okay, you have to write the expression based on the bitwise operator. So this is how we will write or else mention the gates with respect to the bitwise operation. And then coming to the reduction operation. So here, what does this reduction operation means? Applying operator on a single vector. So here, this reduction is nothing but we will be applying the reduction operator onto a single vector. Okay, that means what? If for example, I'm having 10 to 0. So how will I write? R is equals to 0, R is equals to 1, R is equals to 2, and so on, R is equals to 10. So this applying operator on a single vector. So onto this I wanted to apply the operator. So this is how the application of the operator takes place is here. To reduce to a single bit answer. So this is my vector. What am I doing? I'm considering only one bit and I'm applying this reduction operator. Okay, reduction operator onto this so that to get a single bit answer. In order to get a single bit answer, I am applying reduction operator onto a vector. So this is all about that. So module, and here my AND gate. How many AND gates? I am having 8 bits, right? 0 to 7. From 0 to 7, totally 8 bits. 8 bit, that is input 7 is to 0. 7 is to 0 means totally 8 bits A and output is Y. So here assign Y is equals to ampersand A. So ampersand is nothing but the reduction operator. In also the conditional operators we have. For the conditional operator, question mark, okay, and hash. So these are nothing but the conditional operators. So for this conditional operators, we need 3 operands. Okay, 3 operands would be needed. Whereas for different, for bitwise or logical operations, only 2 operands will be needed. But when it comes to negation of A, when it comes to NOT, only 1 operand is needed. Okay. Whereas for conditional operators, we must need 3 operands, A, B and C. So here in the reduction operator, this is how we are reducing. So from 7 is to 0, from totally 8 bits of data, what we are doing using the reduction operator, that is ampersand A. Ampersand is nothing but the reduction operator. Using this reduction operator, I'm getting all this input of 7 data bit inputs onto a single output. That is what? It reduces a single bit operator out of all the 7. Out of all the 8 inputs, I'm reducing it to a single bit operator using reduction operator. This is what the reduction operator is. And finally, I'm terminating with the N module. And coming to the conditional operator. So what is this conditional operator? As I said in the previous slide. So here the conditional operator would be question mark, or else it could be hash, isn't it? So here this is our example of a multiplexer. Okay, we all know what is a multiplexer. Multiplexer is nothing but it's many to 1, isn't it? And based on the selection lines, S0, S1, based on the selection lines, the output would be enabled. Okay. So here in the multiplexer, we have different types of multiplexer, 8 by 1 mux, 16 by 1 mux, and so on. Okay. So under this conditional operator, how this conditional operator would be used or else would be help us to develop in order to write a particular syntax, we will see here. So my module is multiplexer. Okay. I'm giving the name as multiplexer 2. Then input, my inputs are 3 is to 0. So the total is 4 bits of data I'm having, and D0 and D1, these 2 are the inputs. And also I have, and as well the selection lines, input D1, D0 with the selection line, and the output 3 is to 0, Y. Okay. So here Using conditional operator, how can I write the syntax? Assign y is equals to based on the selection, isn't it? There is a condition. If it is 0, 0, if my selection line is 0, what happens? My condition 0, 0, 0, 1, 1, 0 and 1, 1. If my selection line is 0, it will enable A naught or else D naught. And if my selection line is 1, it will enable D1. Okay, so this is nothing but the operation of a multiplexer. So here in the syntax, S and Y is equals to S, the conditional operator, D1 is to D0. So based on the selection lines, my D1 and D2, based on the enabling of the selection lines, D1 or D2, whatever it could be selected. Okay, so I'm finally terminating the program. So end module is a program. So, and when it comes to the figure here, this is a multiplexer, 0 and 1. Okay, D0 and D1 are the input as well as with the selection lines, and output is given as 3:0. Based on the selection lines and the input, the enabling of the bits will be occur. Is it 0, D0 or D1? Finally, next one is using internal signals. So here, internal wires and registers. We have discussed what are the wires and registers. Okay, wires and registers are nothing but these are the keywords where to store the data. Okay, so for example, when you are considering a complex module, what happens? There's a lot of data is need to be stored. Okay, so for such kind of things, wires and registers are needed. Registers are nothing but just to temporary. See, in very long, registers are nothing but it will store the data or else it will pass the data. It's nothing in that. But as per the time being, we will store the data in the registers. When it comes to the wires are nothing but, see, these are the wires, isn't it? So these are the wires. Wires will connect from the output of one circuit to the input of other circuits. Okay, it acts as a connector. Okay, this is what we know for the wires. But here in the particularly when it comes to the gate level modeling, maximum times, most of the times, the wires the wire keyword will be used. Okay, so here this is an example for the full adder. Okay, we all know what is a full adder. Full adder has 3 inputs. Okay, A, B, C, and we have sum and carry as well. Sum and carry bits. So here module, full adder. My inputs are A, B and C in. Okay, and my outputs are C, S and C out, where my inputs are A, B and C in. And then wire prop. So here for the propagation of the inputs or else with the output, what am I using? I'm using a keyword called wire. Okay, just to propagate the input. See, for example, here my 0 and 1. Based on my 0 and 1, for example, I'm considering AND gate. It is 0 and 1. What would be my output? My output would be 0. Okay, and then again I'm considering one more AND gate, that is 1 and 1. So my output would be 1. So here this output of one of the AND gate and the next output of one more AND gate, I'm giving to the OR gate. Okay, so this is nothing but the wire. So the wire will take, or else the wire will carry the output, whatever it is getting from the previous AND gate input. This wire will take out the data and it acts as an input to the one more gate. Okay, so here the propagation, for the propagation of the data from the input to the output, wires will help us to take the data information. So here assign probability of A and B. Assign the property of A and B. A and B is nothing but A, or what is this? This is nothing but the A and B. So here A and B, assign S. S is probability of the C. So here we will see, when you add A and B, you will get the sum, isn't it? You will get the sum and as well as the carry. So here I'm assigning A and B, and then for C in, whatever the info, when you add A and B, whatever the data that you are getting, that one, and as well as the C in, that is one more input. That means what? If my inputs are 0, 0, 0, or else my inputs are 0, 0, 1, what will I do? A, B, C. So first I'll do here, add up. I'll add up these two bits. 0 is 0 plus 0, 0. I got 0. Okay, this is my P. And then with the 0, I'm adding up with C1. So 0 plus 1, 1. So this is my C out. And my sum is equal to 0. So that is what here it is written. And then assign count. C out is equals to A and B, or C in and A or B. Isn't it? This is what we have done. So C out. C out, how we are getting? It is a R of, or else it's a dot product of both inputs A and B, and as well as A or B and C input. One of the two outputs. And then finally ending up with the end module. So as per this, I can write the expression like this. See, I can draw the figure. So A and B given to OR gate. One more C in, right? C in and A or B, isn't it? So this is how I can write, and then finally the end module. So this is all about the internal wires, or this is only the example with the wires. We will see with respect to the registers. So here they're using the as well, this is also as well the registers using the wire. So now it comes to the full adder, A, B, C count, same. Assign count. Count is equals to A and B, or C in and A and B end module, the both and the same. Here in place of wire, I can write register. Register 3:0, comma A. Okay, this is how I can represent with respect to the registers and this with respect to the wires using the internal signals. When you are using the wires and registers, you will be calling that as the internal signals. Using the internal signals, this is how we will write the program. And now coming to the operator precedence. So here we have the operator precedence, and based on the significance of this operators, we have the precedence. Okay, few will have the moderate, the highest precedence goes with the NOT gate, and the lowest precedence will go with the conditional operator. Whereas we can see highest, lowest, high, low, moderate, lower, lowest. Okay, this is how we can give the priority, or as a precedence. Lower, this is also lower, lowest. Same, follows with the same. Okay, and then coming to the constants. So what are these constants? Constants are nothing but the, see, they can be specified in binary, octal, decimal, or hexadecimal. Note, what is a note? Use of underscore in long binary numbers. So here in the long binary numbers, we will be using the underscore. So here, when you look at this table, particular table, these are the constants. And here we have the numbers. What is the first one? First one is 3-bit of data, that is 101. So here how many bits totally? 3 bits. And the base is binary. This is a binary. And the decimal equivalent is 101. What is this 101? 101 is nothing but the 5. Okay, we represent 101. The decimal number is 5, and the stored, how are we storing 101? Okay, and coming to the second one, the constant is unsized. Nothing is mentioned here, right? So it is unsized bit, and it is a binary. B is a binary, and 110. If nothing is there means we have to consider it as 0. So it is 110. So how am I storing here? As it is unsized. Okay, there's no particular size. So for that reason, what am I doing? I'm constantly considering all the bits 0. Okay, all the zeros, and then finally 11. So here this is a 8-bit, and this is a, when you observe here, this is a D, isn't it? So this is a 3-bit of decimal. So here 3 is a 3-bit, D is a decimal, and 6 is a equivalent, decimal equivalent. We know how we'll write 6, 110. Okay, and O is nothing but the octal, and H is the hexadecimal. A and B. Okay, so in the hexadecimal, the 10 is written as 1010, isn't it? So it is A. And 11 is written as 1011, it is B. These are the binary representation of A and B. Whereas when it comes to the hexadecimal, Okay, we represent hexadecimal of A and B is nothing but the 171. So how can we write this 171 in the binary? We need to do the LCM so that we will get, we will convert from binary to hexadecimal. Okay, binary conversions. Already we have discussed about the conversions from binary to hexa, octal to hexa and so on. So, 42, this is the unsigned bit. So only we will see here only the number. Okay, so this is an unsigned bit. But as it is a 42, it's a decimal bit. The decimal equivalent of 42 is, this is how we will be mentioning the 42. This is a conversion of the bits from the decimal to octal or else from binary to decimal. Decimal to binary is nothing but this is how the data is been converted from decimal to binary. Okay, these are nothing but the constants. And we will see the hierarchy. When it comes to the hierarchy, instantiate other modules in your module. So what is meant by hierarchy? As I said, if you are considering any combinational circuits, in the combinational circuits, you will see many kinds of or else many number of modules. Okay, all the modules arranged together forms a combinational circuits. For example, these are the few modules. M1, M2, M3, M4 like. So it is nothing but the accumulation or else the when all the modules are connected at some point and forming a combinational circuit. So here we will see module 1. Sometimes what happens, if for example, this is my basic module. This is my basic module, module 1. So what am I doing here? I do have module 1, which is a basic one, and also that module is preoccupied onto our module 2, and then it is occupied with the module 3, and then this for module 4. So here I could see the totally 4 modules. Okay, one over the other. So that is nothing but the hierarchy of the under module concept. So instantiate other modules in your module. So how can we instantiate other modules? See, these are the other modules. This is the actual module. Onto this actual module, I want to instantiate the other modules. That means what? Under M1, I want to instantiate M2, M3, M4, and then M5, M6. Okay. So this is what I need to finally instantiate other module all together onto this module. That is nothing but the hierarchy. So here if you see module, multiplexer, I'm considering the multiplexer. Okay, so inputs are D0, D1, D2, D3, and as well the selection bits, output is Y. So here, what am I doing? I'm using the internal connection as via. I'm considering the via 3:0. So based on the selection lines, we can say whether the output is going high or low. So here I am representing high or low. So totally, we are talking about the hierarchy onto the module concept, right? So here module for low module D0, D1, S1 and low, and high D2, D3, S0 and high, and for final marks low, high, S1 and Y. So if you observe here, there are the modules. The modules have been represented for each and every particular multiplexer. Okay, with the representation of the high or low or medium or moderate or as a final one. So here, how many totally? We have 3 modules, right? 4 modules actually we have. So module with a low and module with a high multiplexer final considering, and module with a final multiplexer. So this is how we are representing. See, this is nothing but the mux 1. This is mux 2. And finally, the output of mux 1 and mux 2 giving to the input. That is what this is nothing but the hierarchy of the modules. First of all, finding out the module 1, whatever the output is you are getting, giving as an input to the another module. Similarly, module 2, what is the output you are getting? Similarly, giving as an input to the other module 2. So finally, in the module 3, you are getting a single output which is comprised of module 1 and module 2. Okay, so finally at the module 3, I'm considering all my inputs which are coming from the module 1 and 2 and then giving the output, obtaining the output. So this is nothing but the hierarchy under the module concept. So instantiate other modules in your module. How can we instantiate other module? Same, considering the module, multiplexer, input, output, and output. How can you see using conditional operator? Assign y is equals to my selection lines. Based on the selection lines, the output would be decided, right? So D1 is to D0. So this is a previous example we have discussed in the previous slides about this, but particularly here about the hierarchy or else instantiation of the modules. Okay, different modules are coming under one single module. We'll consider this as an example. And what is this sizzling? Bit swizzling. So this bit swizzling is nothing but sometimes useful. This bit swizzling, sometimes it is useful to work on a part of a bus or combine different signals together. Use bus notation. So here bit swizzling, it says that sometimes it is useful to work on a part of a bus. Okay, we all know what is a bus. So sometimes what happens, to some part, okay, to some part, as it is a bus, it consists of number of wires which carries the information or the data. Okay, number of multiple lines of buses, multiple lines of wires are accumulated on a single wire. Single wire is nothing but the bus. So here, some part of a bus, useful for some part of a bus, or combine different signals together. So these are the different signals, isn't it? So these are the different signals together using bus notation. How is? Here we have considered module. Multiplexer 8, input of that is totally 8 bits of marks, that is 8 by 1 marks, input and output 7:0. And then here, what am I doing? Buzzer. As I said we will consider only one heart, or else it works on a part of a bus, right? So here, low significant bit marks D0 3:0 and most significant bit 7:4, D1 and S1. So here if you observe D1, D2, D3, these two are my input and these are my output. So output, how am I getting? I'm considering one more multiplexer. The same way, what am I doing is, I'm just sending with, I'm considering the multiplexer with the low significant LSB bit and MSB bit as well. Okay, so by considering this MSB and LSB, and then finally based on the selection lines, my output would be observed at that particular multiplexer. Okay, so this is the bit swizzling. The bits are getting swizzled based on the highest priority and as well as the lowest priority. Most significant as well as the least significance bits. So sometimes, see, as I said a part of a bus, or else to combine different signals together, isn't it? Now previously we have discussed based on the based on the bus vector notation, right? So bus vector notation means all the buses, all the inputs all together, 7:0, totally 7:0, all the 8 bits at a time, they will divide among themselves based on the priority, and then finally they'll get the output, depends on the enabling of the selection bit, isn't it? And now we will see using the concatenation operator. We all know what is meant by concatenation. It is nothing but the combining. So here using concatenation operator, how will write module 1, input A and B, output upper and lower, assign. Okay, now I'm concatenating both the bits, upper bit and as well as the lower bits in the output. So assign concatenation. Always remember the concatenation is like we will write the concatenation bits in the flower braces. So concatenation bits upper and lower. So for this A and B, okay, A star B, and then finally with the end model. So here the bit swizzling is done based on the using the concatenation operator. And then registers. Registers is edge triggering flip-flops. We all know what is a register. Registers are nothing but they are the storage devices. They store the bits of information. So under the register, using flip-flops or latches, we can store the bits of or is the data, right? So here when it comes to the edge trigger flip-flops, always use reset of some sort. So particularly for the set and reset, in the flip-flops we have set and reset, right? Or else delay latches for delay, D-latch, or else for SR latch. Whatever we have, the different types of flip-flops, the set and using the set and reset, the output will be enabled. So here, module flip-flop, okay, module flip-flop, input is clock, reset, and as well input is totally 4 bits of data, and output is registered Q. Okay, so clock, reset, input D is to 0, and then finally the output. Okay, this is a D flip-flop we are considering. So as it is an asynchronous set, in the reset we have two kinds of resets, asynchronous resets and as well as the synchronous reset. So for this asynchronous reset, we are, see, always at the rate. Always is nothing but is a keyword when you are writing the program under behavioral modeling. So under behavioral modeling, using the keyword always at the rate. Okay, we represent the always at the rate under behavioral modeling. So this particular program or this particular syntax or it's a program is based on the behavioral modeling. So assign always at the rate, positive edge. So as we are talking about the edge triggering in flip-flop, we see two kinds of triggering. Positive edge from 0 to 1 and the negative edge from 1 to 0. Okay, 0 to 1, 1 to 0. This is the negative edge and this is a positive edge. So always at the rate, positive edge clock, positive edge reset. If reset Q is less than or equals to 4 bit, if else, see here we are using the conditional operators, right? By considering the conditional operator, if my reset is equals to less than or equals to 4 bit, then also if it is 4 bit, then my output would goes as well normally. If not, if else, if it is 4 bit, if else it is D. Okay, then finally ending up the module. So here always using always for the asynchronous reset. For asynchronous reset using always at the rate, that is the syntax is following or as a program is following under the behavioral modeling. This is how we will write in terms of the registers. Okay, and also this is this is based on the synchronous reset. The same example we have considered, but in the synchronous reset. In the synchronous reset, always at the rate pos edge. Okay, here you will see positive edge reset. Positive edge reset is already we have initialized positive edge clock and positive edge reset. Both we have initialized, right? When it is in the asynchronous reset, when it is not with respect to time. Okay, and even different times we need to enable or we need to clock switch on at different times. Then we must represent always at the rate positive edge clock and positive edge reset. But when it comes to the synchronous reset, mention we are just initializing always at the rate positive edge. Okay, as it is a synchronous reset, it syncs with the respecting time for different times. For t is equals to 0, for t is equals to 1. Okay, for this synchronous, constant, continuous, there is only possibility that we can mention is only the positive edge clock. There is no need to mention the positive edge reset or positive edge reset. Then, if same reset less than or equals to 4 bits of data, if it is going it's well and fine, or else Q is equals to less than or equals to D, and finally ending up with the end module. Okay, so this is all about the few examples, design examples under the behavioral modeling. Okay, whatever we have studied in the previous sections of module 3 behavioral modeling, that is how to write a particular syntax based on the comments, based on the operators, okay, and also based on the continuous assignment statements, and as well based on the keywords, wire, net, okay, and all the connectors, based on the comments, based on the keywords, based on the operators, how to write a particular syntax in the behavioral modeling. This is about the examples. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.